Okay. Oh, good evening, everyone. It's a pleasure to come back to you people again on a live session. I could see some questions are there. Okay, Sony and Pratibha. Who else is there? I saw a couple of questions posted. I shall answer you. Pratibha has asked about paper pattern. Okay, why do you worry about pattern? Okay, what you can do is if you study well, no matter what kind of pattern is given for this exam, you should be able to answer, right? Okay, so the focus should be about understanding the basics. Once the basics are cleared and understood properly, and no matter how the questions are asked, you should be able to answer. Is that right, Pratibha? Any comments are there? You can write in the chat box. Perhaps NPTEL has already given you about the paper pattern. It consists of uh, multiple correct answers, multiple choice, two types, and also uh, numeral questions. Okay. So these three patterns with these three sections will be there. Okay, one with multiple choice and single only correct answer questions. And then uh, fill up the blank. That's mostly numeric question type. Okay. Okay, another question is about uh, thiocyanide, right? So thiocyanide, okay, it shows linkage isomerism. S can also coordinate to metal center, and also N can also coordinate to metal center. Okay, yes. In probably there is a mistake in the spectrochemical series. Some place I must have shown sulfur when it's coordinating to the metal is a strong field ligand and N is weak field ligand. That's not correct. And when S is coordinating, it is weak field, okay? And when you look into the rank of SCN with respect to S and N coordination, N shows stronger coordination. That means it comes on the right side in the spectrochemical series, whereas S comes in the beginning of the spectrochemical series after halides and OH and something. Okay, is that clear? So consider when N is binding, okay, that should be at the right side, and SCN and NCS are given. Okay, the ligand field of NCS is greater than SCN. Is that okay? Why that happens? S is being, N being negatively charged. What happens? S electrons are pulled a little bit away from it. As a result, what happens? It falls into weak field ligand type. It falls into the left side of the spectrochemical series, whereas N being more electronegative and also charge is there, and also it can also can act as a little bit of back bonding ligand, very similar to cyanide anion. Okay, so it comes in the right side of spectrochemical series. Yeah, so any other questions, you can always write in the chat box. I would be more than happy to answer those questions. Oh, okay. These are called Mulliken symbols. Okay, Mulliken symbols. For example, I have given a table. You can see in the Mulliken symbols for different point groups. Okay, the Mulliken symbols corresponding to orbitals such as s orbital, 3p orbitals, px, py, pz, and then 5d orbitals are there, dxy, dyz, dzx, and dx minus y square and dz square. For them, okay, they will carry different Mulliken symbols, okay, depending upon different point groups. Okay, I haven't opened my lecture here to show you that one. You can have a look at it. One thing I shall tell you, if you have the table handy, you can open and that look into it. For example, s orbitals are spherically symmetrical. Its okay, Mulliken symbol doesn't change no matter which point group you are referring to, which geometry you are referring to. They remain as A1, A1G. Okay, or on the other hand, for example, if you consider square planar complex, if you recall, the valence bond theory and the type of hybridization, that is sp2d. That means one of the d orbitals we are using and s orbital we are using. Now, instead of 3 orbitals that we used in octahedral complex, we are using 2 orbitals from p block. So that is, say, p, x and py. Okay, in that case, what happens? It's sp2d. So that means basically in square planar complex, the degeneration of p orbitals is no longer observed. Instead, it splits into 2 levels. One is pz, one is px and py. So then that means basically you will be having 2 different type of Mulliken symbols. Px will be different, pz will be different, and maybe px and py can have the same Mulliken symbol. This is how it goes. And then if you look into octahedral geometry, entire d orbitals will be split into T2g and EG. That means T2g consists of dxy, dyz, and dxz. And then if you look into the Mulliken symbol, all of them have T2g. Okay, dxy, dyz, and dxz have T2g Mulliken symbol. On the other hand, EG consists of dx minus y square and dz square. Both of them have EG Mulliken symbol that you can see in the table. Okay. And then p orbitals are degenerate, because if you consider again valence bond theory, we talk about D2 sp3 or sp3 D2, and they still degenerate. As a result, they have T1 new Mulliken symbol. That's the reason you can see px, py, pz, all of them have T1 new Mulliken symbol. This is how it goes. To understand better, you have to be familiar with group theory and character table. From there, you can draw much more information about those entities. Harikesh, how are you? You were asking many questions, and I think I answered most of your questions, I think, right? One of you asked about pairing energy. Is that right? I don't know who asked about pairing energy. And why in case of low spin, Arup, how are you? Okay. Yeah, so what would happen is, for example, say D1, D2, D3, no issues. All of them will be in octahedral geometry I am referring to. All of them will go to T2G level. And then the fourth electron in the high spin complex, fourth one will go to EG orbital, EG star, I would say. In that case, what happens? Why that happens? You know that here we have to compare pairing energy versus promotional energy. If the pairing energy is much more larger in the magnitude compared to promotional energy, they will be going to higher orbital EG, so that we have 4 unpaired electrons that can continue until it is D5. When it comes to D6 system, whether it is high spin complex, what happens? It has to come to T2G only. Okay, no other option is there. Because pairing energy is much smaller than higher than but nevertheless, it's a high spin complex. What would happen is it would be getting paired here. As a result, what happens here, you should not consider the pairing energy associated with that pair here. So that's the reason I think D6 system, you get minus 0.4 as a delta O for the same reason. And of course, if you take a low spin complex, yes, you have to force them to stay in the T2G instead of going to EG. In that case, you have to consider 3 pairing energies. Is that clear now? Yeah. Any other doubts? Yeah, I understand that. I think about SC and the NCS coordination, linkage isomerism, I think it's clear now, right? Yeah, yes, when it is S is binding, it's a weak field ligand. When N is binding, it's strong field ligand. That you should remember. Yeah. You can bother me now, okay? Several minutes are left now. I'm glad to inform you that I am coming up with another course on spectroscopy. The title is Interpretative Spectroscopy. So in this course, without delving deep into the theoretical aspects, I shall tell you how to interpret different spectra such as NMR, IR, and mass spectrometry without having solid theoretical background. So in case of NMR, I shall touch upon apart from 1H and 13C, 31P, 19F, and most of the elements in the periodic table do have non-zero nuclear spin value I. As a result, what happens? Many of them show NMR activity and NMR active. I shall look into most of these nuclei and discuss about multinuclear NMR system and how to characterize and how to use it as a powerful tool to understand the reactivity and properties, and also if there are application any. All those things can be really understood by looking into this multinuclear NMR when it is combined with IR and spectrometric data. So I shall start maybe next week and probably January 2024. So that course will begin for the first time. And I'm sure you all enjoy that course. It is very useful. It's going to be very useful, especially if you're planning for exams such as JOM exam, GATE exam, or CSR exam, or planning to start PhD, or want to get into R&D unit, or go for forensic studies, or go into biochemical aspects, biochemistry, or material science. So NMR is inseparable from all these aspects. From that point of view, I will be coming up with very interesting and useful examples to make you understand in an easy way how to analyze and interpret and elucidate the structure of compounds, whether natural products or compounds you come across in chemistry or in biology, etc. Okay, covalent electron count method. Okay, I told you this electron counting or 18 electron rule or effective atomic number, also called a Sidgwick rule, is very, very important in understanding the reactivity of metal complexes and also their possible utility in homogeneous catalysis for organic transformations. And nowadays, if you just look into it, most of the organic chemists, they are using metal complexes or coordination compounds or organometallic compounds in one or other way to do organic synthesis in the name of homogeneous catalysis. So to have a better understanding of mechanistic aspects and how metal is doing these tricks of bringing two entities on its coordination and then coupling them and sending them out with selectivity, regioselectivity, and all those things. For that one, this electron count comes very handy. And here, what is electron count? If you look into p block elements, we talk about octet. That means boron, it starts from S2P1 and we end with inert gases S2P6. That means P1 to P6 will be keep on adding until they have the electronic configuration of S2P6. That means 8 electrons in the valence shell. That is octet. That means all main group elements have a tendency to have 8 electrons in their valence shell that we call octet, and the capacity is 8 electrons. When we go to transition metals 3D, 4D or 5D, what we have is we have additional orbitals coming from D. That is 5D orbitals are there and their capacity is about 10 electrons. So now valence orbitals can accommodate as many as 80 electrons. So that means all metals, when they undergo complexation, have a tendency to have as many electrons as possible so that they mimic the next inert gas. Okay, when you count totally everything along with core electrons and valence electrons, it would match the next inert gas, that is called effective atomic number. And the 80 electron rule means it is basically S electrons are 2, P electrons are 6, and D electrons are 10. Okay, all metals, ions are neutral metal atoms. They combine with suitable ligands in such a way that they try to have 18 electron configuration. This is called 18 electron rule. That means you can ask me question, is it must for stability? Not necessarily. If every complex had 18 electron configuration, probably these compounds would not have come very handy in many applications. Okay, that is the reason we also have 14 electron complexes, 16 electron complexes. They are quite active and also very useful in catalysis and other applications. Now, how to count these electrons? That's very simple. We can adopt two methods. One is neutral method or covalent method. Other one is ionic method. In neutral method, what you should do is you take simple example of chromium hexacarbonyl. Okay, chromium hexacarbonyl, whether you take ionic method or neutral method. Neutral method is also known as covalent method. In both the methods, okay, we arrive at the same method because here we don't have any ionic ligands. Metal is neutral, zero valent metal, and ligands are neutral. So here CrCO6 means chromium, if you take, it has 3d4 4s2 or 3d5 4s1. That means 6 electrons are there in that one. And then 12 electrons are coming from 6 carbon monoxide. So that will become 18 electron. This is called neutral method. Of course, ionic method doesn't come. Ionic method also, metal is zero valent. So 6 electrons and 12 electrons are coming from the carbon monoxide ligands. It becomes 18 electrons. So if you take some examples such as, let me write it. Okay, so let us consider this example here. CP2, ruthenium, Cl, PPH3 twice. Okay, so let us look into this example. Okay, here I will show you using both ionic method as well as covalent method. Let me go with first neutral or covalent method. Both are same. So in this one, as I said, you should not worry about the oxidation state of the metal. What you should know is you should just know how many electrons are in the ruthenium valence orbital in the ground state. So you know that ruthenium comes below iron. So iron, ruthenium, osmium. So here this is 3D, 6, 4s2. Okay, and here it is 4D, 6, 5s2. And here 5d6, 6s2, right? So that means we have to worry about 8 electrons. So 8 electrons, I will put it here. And CP versus, excuse me, CP versus CP minus. CP minus you should not consider here. Neutral method, CP should be considered. CP is 5 electron donor. CP minus is 6 electron donor. So here 5, 2 into 5. Okay, and now Cl in the neutral method is 1 electron donor. Only in the ionic method is 2 electron donor, Cl minus. Okay, Cl minus will be something like this. Okay, so now it is 2 electron donor. In absence of negative charge, a dot is there. Okay, so now it is 1 electron donor. So 1 electron donor, and ppH3 is a neutral ligand. So 4 electrons are coming. So if you count now, okay, so 10 plus 8 plus 2, 10, 10, 15. Okay, 10, 10, sorry, 8 plus 10, 8. Oh, okay. Oh, so, it is not CP. Okay, this is CP. Okay, CP2 cannot exist like this. It is 1 CP. 1 CP minus basically it is 5 electrons. So 13 plus 1, 14 plus 1. Okay, it is 18 electrons. Okay, this is 18 electrons is there. So it satisfies 18 electron rule. Okay, the CP RuCl. Okay, the structure will be something like this. Cl. Okay, so this is covalent method. So 8 electron there. Now look into anionic method. Anionic method, you should know the oxidation state of the metal center. So ruthenium Cp is a negatively charged ligand and chlorine is also negative, so that here 2 electrons are going, one each to Cp group and this one. So now we have 6 electrons are there on, because ruthenium is 2 plus. Okay, now this is 6 electron donor, Cp 6 electron donor, and chlorine is now chloride ion, so 2 electron donor, and there is no change in the ppH3, 4, it becomes 18 electron. So this is how you can do counting using both ionic method as well as a covalent method. Is that clear? Chart. Okay. Is it clear now? Yeah. In case of bridging, okay. In case of bridging ligand. Oh, okay. You are referring to that. Okay, 4 carbonyl compound, right? Okay, so let me come back to that one. Yes, I will answer about that one. Okay, yeah. Take a new one. This one, here. Oh, next one. Select next page on. Okay. Okay, so let me take that example here. I think this is the example, right? M I put here, and another M, and another M, something like this, and each one has a CP group. And now we have CO, CO, and CO. So something like this, right? So here, of course, electron count also I can tell you. Here, what is M? I already answered. And here you can say, well, it is a bit difficult. It's not all that difficult to predict, because what happens, each metal has 3 metal-metal bond. Okay, so that means 4 such metals are there. We have that many metal-metal bonds into 3. But here what happens, 2 will be sharing. For these things, we have to consider 12 electrons are needed to have a metal-metal bond, 3 metal-metal bond among 4 groups. Okay, so that means 12. And then if I say this molecule satisfies 18 electron rule, then 4 metals are there. 4 metals means each one is satisfying 80 electron rule, means it should be 72. Okay, in 72, you remove 12 electrons. Okay, 12 electrons are coming from metal-metal bond. You should remember metal-metal bond, within the whatever the valence electrons we have, we will be adjusting to give stability, very similar to octet rule what we do it. For example, if you recall CO group here, okay, we have only 10 electrons. In 10 electrons, what happens? Electrons will come and sit here, and 2 electrons will be here, and 2 electrons will be here. Total 6 electrons are there. In 6 electrons, when they are shared between CO, okay, octet is satisfied for both. Okay, yes. and not simultaneously, okay? Not simultaneously, they cannot satisfy. For example, when I'm counting this one, it will be left with only 2 electrons. Similarly, when I'm considering this one, it will be left with only 2 electrons. But although both of them are satisfying, we do not have 16 electrons. Okay, so the same thing is true in this case also. Okay, when you talk about metal-metal bonds, say 34 electron system like CO2, CO8. Okay, if you look into why it undergoes dimerization, because it's a 34 system. If you consider CO2, CO8, what happens? We are coming from 16 electrons are coming here and 18 electrons coming from 2 cobalt. So what we have is 34 electrons. So 34 electrons are there. There is a short of 2 electrons to have, okay, 18 electronic configuration. As a result, what happens? CO-CO bond will be there. When CO-CO bond is there, again, when I'm counting 18 for this one, this will be having 16. And when you are counting 16 for this one, this will be having 18. So you should remember, but at a given time, okay, when this comes, both of them will satisfy. In the same way here also, so 12 electrons are involved in making this many metal-metal bonds between 4 metal centers. So 12 electrons, you remove it. Now we have 60 electrons are there. When the 60 electrons are there, 4 metals are there. 4 metals means it is 15. So that means each one will be 15. Okay. Yes, each one is 15 means now let's try to identify using neutral method. So 15 electrons are there, each one. Okay, let us try to put the number of electrons for each metal. So now we have is 5 from CP. CP is giving 5 electrons, and then 4 CO groups are there and 4 metals are there. So each one will get 2. Okay, so that means 7 are done. Now what is the shortage is 8. Okay, it becomes 15. So that means basically the metal should have a valence electronic configuration of 8. 8 means if you have still doubt, you should consider first 2 electrons. Okay, yes, 2 electrons. Then how many electrons are left? 6. Then you can put on 6. And this would come to, okay, if I say specifically this is a 3D metals, then this is iron. It is a 4D metal, then it is ruthenium. Then it is 5D metal, this is osmium. So this is how you can solve it. Now, the question is, CO is bridging, yes. CO, when it's bridging, you should remember, it's not acting as a 4-electron donor or 6-electron donor. Whenever it's bridging, whether it's acting as a terminal ligand, whether it's acting as a bridging ligand, whether it's bridging 3 metal centers or it is bridging 4 metal centers, it's always a 2-electron system. You should remember, okay? How it happens? For example, let us say this metal is there, this metal is there, and then CO, okay, this C is there, this is the one lone pair, so this overlaps something like this. This is very similar to what we come across in B2H6, okay, bridging, 3-center 2-electron system. This is what exactly happens. So it is not, okay, acting as, okay, a 4-electron donor. Carbon monoxide is always a 2-electron donor, and this is how the bridging will be there. That means basically this orbital, whatever is there, it overlaps with all of them. Okay, so something like this. Is that clear? So now it is iron. Okay, very easy to tell. What you do is, if I say it satisfies 18 electron rule, so that should come, that hint should be given in the question. If I say this cage compound given satisfies 18 electron rule, okay, and then the structure is given so that you can count how many metal-metal bonds are there, and then identify the metal. Then the moment I say all of them are satisfying, I should immediately consider 18 for each one. 18 into 4, 72 are there. Out of 72, 12 electrons would go because they are happening within. Okay, so that means 60 will be left. Out of 60, if you distribute 15, that means each metal would be having 15. Each metal will be having 15 electrons. Now you take the ligands are known, CP is known, CO is known, unknown entity is, now it's just balancing. Okay, metal 15 is known, 15 equals CP5, okay, plus 2, okay, plus M, unknown entities, say M, okay. So now, now M is there. So M equals, now you can calculate 8. Okay, and 8 is there. If you have still doubt, first 8, whatever the number comes, M, first put S2. Okay, now 6 will be left, D. So this is what happens. Is it clear? Okay. No, the yeah. Chart box. Close it. Start. Okay, tell about delta one. Okay, I think I had explained very nicely with even cartoons. Look into metal-metal bond formation. For example, let us consider a D4 system. Okay, D4 system is there, Re2Cl8 2 minus. When you take Re2Cl8 2 minus, oxygen state of rhenium is +3, right? +3 is there, +3. So that means how many electrons are left in the d orbital? 4 electrons are there. Okay, and then it's a square planar complex. Okay, now let me go back to again to the blank sheet. I will explain you. Okay, it's okay. So this rhenium is like, you have to consider square planar geometry. All these compounds, wherever we come across delta bond, we would be having invariably square planar complex, and they are dimeric in nature. So when you put like this, okay, so these are all Cl. Let's not worry about charge now. Okay, so now again, now basically what happens, if you imagine d orbitals, dz is like this. Okay, right? It is like this. Now, if I'm considering this D4 system, right? D4 system and D4 system, how to arrange these electrons? First, what would happen? This d orbital is 2 d orbitals are there. Okay, dz square are there. So they overlap. When they overlap, okay, so something like this. Okay, so then here one electron is there. So here, if I take so something like this, 4 electrons are there. First dz square has 1 electron. So it comes here and it comes here. So now it is paired up. So this is your sigma bond. Okay, that means head-on collision is there. So this is your sigma bond happens. Now if you imagine here, dx z, dxz is okay to perpendicular to the xy plane, and then orthogonal is dyz. Okay, so these two, when they come like this, so now if you just imagine here like this, and another one is like this. Okay, so now basically, can you see here? I think you should be able to see. Okay, so if you see here, okay, so something like this, it happens. Okay, so now the dz square, okay, you get a sigma bond, 2 electrons are gone. Now dxz and dyz. Okay, so dxz and dyz will be like this. One is like this. So this is a pi overlapping. One is like this, another one is like this. Okay, so that would come here. So something like this here. Okay, if I write another one is little bit like, okay, so these two will come here, and then you have another one like this. Okay, and like this. So here, what you have, you will be having 2 pi orbitals will be there. 2 pi orbitals. Okay, 1 sigma. And then what is left now? 1 electron is left. Okay, in this one, only dxy is left now. Okay, dx square y square is not there. So whatever the orbits we have in this one is for metal-metal bond formation are only dxy, dxz, and dyz, and dz square. You ask me why x square y square is not considered. Well, x square y square is utilized for metal to ligand bond formation. If you recall from valence bond theory, what is the hybridization? It is sp3d, sp2d. D orbital is dx minus y square in the plane. Okay, so that means dz square has 2 electrons. So that means since d X square and Y square is utilized in metal to ligand bond formation. Here you are not considering for metal-metal bond formation. It is not available. So now what is left is only dxy. So dxy will be something like this. Okay. So something like this. When they overlap here, so they will be partially overlapping. Okay. So that means basically, I showed you this is, okay, this is your dz square. Okay. And then this is dxz. This is dyz, and then now you have dxy. So dxy have no option other than overlapping like this. Okay, they overlap like this. Okay, this is sigma, this is pi. Okay, this is pi, right? This one is pi, this one is pi, or orbitals. I think I have. Okay, I will show you. Yeah, if you just consider here, you can see, assume this is okay. So this one is dz square, right? Dz square is something like this, okay? And now if I consider other portion is there like this, okay? This is assume this is a dxz, okay? This is dxz will be overlapping like this, and dyz will be overlapping like this. Okay, dyz will be overlapping like this. So two are here, okay, something like this, and then this is like this, okay, dxz and dyz, and this is dz square sigma, and this one is pi, okay, another one is pi. Then what is left is dxy. Dxy, now if you move rheniums towards each other, they will be overlapping like this. This you never heard of. It will not come across in p block elements in or any other. Okay, this is called delta bond. So delta bond will be xy will be like this. They'll be overlapping. Okay. So here, that means here we have two electrons. Okay, so coming one electron here, one electron, one electron. Now dxy has one electron and this. Okay, so this is your delta bond. So that means basically between rhenium and this one we have. Okay, yes. Is that clear? Of course, you can ask me next quintuple bond. Quintuple bond, in order to have quintuple bond, 5 bonds, we should release dx minus y square also. That means if we have all the 5d orbitals are readily available, and if we have d5 system, in that case, what happens? Molecule should be linear. In this case, I can utilize all 5d orbitals for bond making. Here again, another delta will be coming. Again, that would be dx square minus y square. And here, two more electrons will come. So now with the bond order will be 10. This is called quintuple bond. For example, in case of chromium or tungsten, I have shown that the example, you have 5 electrons. This is quintuple bond. Okay. And this is quadruple bond or delta bond. So here you have two delta bonds. Okay. One sigma bond, two pi bonds, and two delta bonds. And of course, here delta star will come and pi star will come, higher energy, and sigma star will come. Is that clear? So, yeah, close. Oh. Yeah. Is it clear now? Okay, NO3. NO3 is a bidentate ligand. Okay, and you have uranium to oxygen 2 double bonds. That means you have something like this. Okay, video is okay. I think. Can you hear me? Can you hear Ashwin or Ashwini? Or it is bit going slow. I think it is replay is going on here. Okay. Okay, so in this case, it's not live. Okay. Okay. Yeah. If you take uranium, in axial position, you have uranium double bond oxygen is there. And then you have 3 bridging NO3. That means 8 coordination is there. 8 coordination, it can have uh, either hexagonal, you know, um, bipyramidal, okay, right? Or it can also have a square antiprismatic geometry, okay? And can aqua ligands always produce joint? No, yes, not necessarily. It depends what ligand system is. When you consider D4 and D9 electronic configuration, where EG orbitals are unsymmetrically filled, then you can come across Jahn-Taylor distortion no matter which ligands you are talking about. Okay, and whether you take homoleptic molecules or heteroleptic molecules, okay, you come across Jahn-Taylor distortion invariably where you have unsymmetrically filled EG orbitals. For example, if you consider D4 chromium 2 plus, in that case, what happens in high spin complex, you have 1 electron in EG. Similarly, D9 system, copper 2 system, you have 3 electrons in EG orbitals. There, what happens, the degeneration is destroyed, and then you come across Jahn-Taylor distortion. That can happen even with hexa amine compound also. Okay. So all compounds, irrespective of ligands, D4 and D9 electron configuration shows. You can ask me what would happen if unsymmetrically filled T2G. Unsymmetrically filled T2G has less impact, and you may come across very, very weak Jahn-Taylor distortion that can be often can be neglected. Well, so TBP and square pyramidal, how to distinguish them? Okay, if you do not know, right? We have to go for some spectroscopic methods. Let's, for example, FeCO5 is there. FeCO5, of course, FeCO5, if you want to take room temperature NMR to identify whether I have 2 types of carbonyl groups using 13C NMR spectroscopy, it is a bit difficult because even at -50, they can show dynamic process and Berry pseudo rotation. As a result, you may not be able to see. But on the other hand, if you freeze all the dynamic activities, okay, by going to lower temperature, you can identify 3 in the equatorial plane and 2 axial, and you'll be getting 2 different type of signals in 13C. You can identify, and if square planar complex is there, and 4 of them are of one type and 1 of one type, so you should be able to distinguish from NMR as well as IR also. IR also, you can go and see how many IR active bands are there. So based on their point group, okay, you can identify if it is FeCO5 or something like that. You should be able to tell. Okay, you should be able to distinguish them, and whether a given molecule with 4-5 coordination number, whether it prefers square pyramidal geometry or trigonal pyramidal geometry, if you ask me, and always they prefer more symmetric one, and also ligands can also be distributed away from each other in such a way that, okay, your steric encumbrance will be minimum. From that point of view, always tendency is or preference is given to trigonal bipyramidal geometry. But on the other hand, due to various other aspects, we can come across pentagonal square pyramidal geometry also. I think I have listed some of those things in that table where I have given all hybridization and the appropriate examples. I have shown there, you can have a look at it. I have given 1 or 2 examples in that case, I think. Any other questions, Sony, Anu, Arup, Ashwini? So I will be taking another couple of live sessions, okay? And if you have any doubts, collectively you make it and send it to me so that what happens, I can spend a little bit more time, explaining all those things. How can you distinguish between dodecahedron and square antiprism structure? Okay. You see, square antiprism structure and dodecahedron, it is, well, how to distinguish? It's not it depends what kind of ligands we have. Okay, if you have homoleptic molecules are there, uh, we can distinguish by just looking into the structure. Okay, structure can tell you. Okay. Uh, Otherwise, any spectroscopy, yes, spectroscopic methods may not be that useful in differentiating between these two structures. I think we should go for crystal structure, or sometime, yes, if you have different ligands are there and some of NMR active nuclei are there in it, we should be able to tell. Or if you have one or two carbon monoxide or some other ligands which have active IR bands, then we should be able to tell. Among NO, N2 and NO, okay. So N2 is a weak ligand, okay. N2 is capable of acting as a pi acceptor also, but it's a weak sigma donor and very, very weak pi acceptor. On the other hand, NO can be a good sigma donor, and of course, NO has odd electron because of 11 electrons in the valence shell of NO. When you write MO diagram, one goes to antibonding orbital. So then the bond order is 2.5. So it will easily get rid of one electron to become NO plus. And when NO plus is there, to establish a bond, metal has to give one electron. So that means basically, although it's one electron it's giving, in the bent structure, it's actually two electrons are involved in making the metal to nitrogen bond. Just you should remember that one. Okay, it appears like one electron donor, no doubt in it, but to establish a bond, another electron is coming from the metal so that you have a metal to nitrogen bond. Okay, and then this is also a good pi acceptor. Compared to nitrogen, it's a very, very good sigma donor and also very good pi acceptor. Sarita, what is that one bond order of N2 minus? Okay, well, N2 minus, you can see N2 minus will be, you're adding one electron to now, okay, antibonding orbital. It should become 2.5 now. And NO minus, yes, NO minus also same. When one electron is there, you're adding one more electron. So they now they are isoelectronic with oxygen. So oxygen has two unpaired electrons in the pi star orbital. So bonds will become double bond. How to find weakest bond in MO theory? MO theory cannot tell you, okay, about, yes, MO theory can tell you depending upon homo-lumo gap. Okay, if you find out the homo-lumo gap, okay, so that one can calculate using DFT method. Okay, from that one, you should be able to tell, okay, which one is strong ligand or which one is weak ligand. You should be able to tell using very, very easily using MO theory, because it can clearly show the difference, the energy gap between highest occupied molecular orbital and lowest unoccupied molecular orbital. Okay. So that's why it's more effective compared to crystal field theory. So I didn't get what you're writing. Okay. Any more questions? Yeah, okay then. See you in the next live session, so that I would be announcing well in advance. If you have any questions, keep it ready so that we shall discuss, okay, in more detail. No, yeah, see, we are talking about NO and N2. Okay, if you go and add electrons, then what happens? The bond order would change. Certainly, bond order would change. In that case, probably yes, the ligand properties would also change. Okay. In bridging, what bridging ligand? You have some bridging ligands are there, or bridging complex? It's not clear to me. By 18 electron counting, yes, 18 electron counting, by counting electrons, you can see metal-metal bond is there or not. And if the metal-metal bond is there and a couple of bridging ligands are there, then what happens? That would add more stability, and also whether the metal is coordinatively saturated or unsaturated. Okay, usually when each metal is satisfying 18 electron rule, they are coordinatively saturated and electronically saturated. As a result, what happens? They probably will be less reactive, okay, more stable. If you want to use in some application, you should not use such system. You should have coordinatively unsaturated and electronically unsaturated. That's the reason we use square planar complexes of rhodium 1, iridium 1, or palladium platinum 2, where we have 16 electron complex and they have 4 coordination. So that we can go from palladium 2 to palladium 4, or rhodium 1 to rhodium 3, so that we can do oxidative addition, and then we can activate some molecules, and then we can do coupling and other hydrogenation and other organic transformations. Okay. Okay, when it is used, okay, yes. If the coordination number, say preferred coordination number is 6, and if you have less number of ligands are there, in that case, what happens? The bridging will come into picture. Okay, for example, if you take Fe2CO9, when you take Fe2CO9, what happens? Each iron prefer to have 6 coordination, okay, but we have only, instead of 12 carbon monoxide, we have only 9 carbon monoxide is there. In that case, what happens? They bridge in such a way that coordinative saturation comes, and also electrons are also evenly distributed, so that both of them look symmetric. That is the reason if you take Fe2CO9, each iron has 3 terminal, both side, and 3 are bridging like this. 3 bridging are there, and 3 here and 3 here are there. So also they prefer to have symmetric structure. Okay, let me stop today and come back to you in the next session. Okay, keep ready. So we shall discuss more interesting aspects. Okay, then. Yeah, if you have more questions, what you will do is you note it down and post it to me. I can answer, as and when it comes, or I can accumulate them and discuss in more detail. Okay, so that it benefits all. Is that all right? Okay, then. See you all.